So good morning. Welcome to Krishna's classroom. In the last lecture, we concluded by saying that the inner product space is a normed linear space. And once it is a normed linear space, it induces a metric on the space. Therefore, every inner product space is a metric space. So this is what we concluded. And hence a topological space. And we also observed that the Cauchy-Schwarz inequality plays an important role in proving that what we have defined norm induces a length concept. Okay, so the Cauchy-Schwarz inequality is vital in this regard. In fact, we have seen that in R3 it essentially tells you that mod cos theta is less than or equal to 1. Okay, because the inner product in that case talks about the angle between the two vectors x and y, or it gives a measure of that. Okay, therefore we shall now see what are the consequences. So now V is if V is a metric space, now we want to show that, okay, this is what we have defined as the norm of V to the power half. And you see that the distance function that you have is d of uv this defines a distance function. Now this is what we have found. Therefore Vd now you see that if V is a metric space, then V cross V is also a metric space. Okay, and if you look at the addition, see what are the vector space operations? Now what we want to assert is that the vector space operations are continuous. What do you mean by that? That is, if you take plus as a map from V cross V to V, defined by the ordered pair plus operation maps to U plus V, and then dot is a map from defined by alpha V, the ordered pair alpha V gets mapped to alpha V. These are the maps that we have. We want to assert that both these are plus as well as scalar multiplication are continuous functions. From where to where? See, V is a metric space, therefore V cross V is a metric space. So also C cross V is a metric space with the usual metric that you have on C, and there you can also take R, C or R. Okay, so remark. Is a real inner product space. C is replaced by okay. So what is the meaning of that? So this is the following. This means that the vector, see, you have now on V we have an operation addition. We have an operation scalar multiplication. Okay. So you are asking whether it's a continuous map or not. From V cross V to how do the, see, the topology, there is a topology induced by the metric, and how does this topology gels with the two operations, namely addition and scalar multiplication. Now this problem is a very general problem. See, whenever you induce or introduce multiple structures on the same space, you ask how do they work together. For example, you have addition, you have scalar multiplication. Okay, then you ask how do they work on this, and you can see that the moment you introduce an inner product, you are also saying what happens if you take sum of two vectors and scalar multiple of a vector, how does the new operation go with it, and that is what we define. And here we are saying something concrete because we have now a topology to play around. So V cross V is a topological space, V is a topological space, and the condition that is desirable is that the addition has a map from V cross V to V, and the scalar multiplication from C cross V to V are continuous operations. So what do we have to do? So the first thing that we prove is this: xn converges to x, yn converges to y, implies x plus y. It's quite easy to prove because you see in every normed linear space it does happen. See, what you have to do is to take the distance between x1 plus y1. So this is from this estimate. By the triangular inequality, this is now you know that xn converges to x, yn converges to y. Therefore, by choosing n sufficiently large, you can get, so given any epsilon positive, you can choose n sufficiently large such that norm of xn minus x and norm of yn minus y is less than epsilon by 2. Therefore, this can be made less than epsilon by 2 by choosing n sufficiently large. Therefore, it is continuity. So, continuity follows. The second part is about the scalar multiplication. Whenever alpha n goes to now this means that here the metric that you have is this. The distance between two complex numbers is the absolute value of the difference between these two numbers. And here of course the whatever be the metric induced by the inner product. Okay. And that's also again easy to see from this inequality. You add and subtract a few terms and then estimate it. So you have got alpha n xn estimate this. So you see you have norm of by triangular inequality. This is now this is of course you have now you see that this is bounded because xn converges to x. Therefore, it is bounded. So, also alpha n converges to yeah. So, you see that mod alpha is there, and therefore, you see that you can make, you can choose n sufficiently large. Given an epsilon, you can choose n sufficiently large such that sum of these two terms is less than epsilon. Okay, so use this. So use the boundedness that is boundedness of norm xn is values of. That follows from the convergence. Therefore, you see that the continuity of these two operations are assured. Okay. Now you also see the following, that is, show that that's also quite easy to see. I leave this. I mean, that's quite simple to work out. So this is, in a way, you are making sure that the vector space operations are continuous with respect to the norm. Therefore, the inner product that you have introduced and from which the norm is derived, okay, induces a topology that is compatible with the vector space operations. Well, I want to make a remark here. The remark is this: there are situations in analysis where one would have to introduce topologies not derivable from a norm. Okay. That means we will have to go beyond what are called normed linear spaces in certain circumstances to for developing mathematical analysis. One situation is when you introduce the concept of a distribution. It is in the distribution theory. We would have to introduce non-normed what is called topological spaces, which are linear spaces, but the topology is not induced by a norm. So such situations arise. I am not going into the details of that. And in those circumstances, what you have is you have a linear space. Abstractly, this is what you have. You have a linear space, which means there is a concept of addition and scalar multiplication. And then you are having a topology on that. So if V is a topological space, V cross V is a topological space. Therefore, addition can be looked upon as a map from V cross V to V, and scalar multiplication can be looked upon as a as a map from C cross V to V. Now, what we demand for smooth working, that is the minimum demand that you make on the choice of the topology, is that these vector space operations are continuous as maps from V cross V to V and C cross V to V. Now, this is a very natural thing that you demand. Then you see that your life becomes very simple. And such spaces are what are called topological vector space. So you see that every inner product space is a normed linear space, every normed linear space is a topological vector space. But there are topological vector spaces which are not normed linear spaces. Okay? So that's just a caution. So we will make just a note of that. Maybe it will be a sort of pointer to what we want to do. Course of the development of mathematical analysis. There are situations which demand introducing topology on the space. On the space which is not derived that is, it is not a norm topology. This one comes across while introducing the notion of the concept of distributions. Like the so-called Dirac delta functional, I mean, I don't want to call it a function. Okay. So, to legitimatize objects like Dirac delta functional, we need to talk about a normed linear space with a topology which is not something that comes out of a norm. Because if you work in a normed linear space, in that case it becomes inadequate. And this is what is called the topology induced in that way on function spaces is what you call an inductive limit topology, which is not derivable from a inner product space. And there what we demand is that, so in those circumstances what we demand is that the vector space operations are continuous with respect to the topology that we have introduced. So I will make note of that, and this is a pointer to what you would have to expect later when you go further to study mathematical analysis. So we are not right now going to say more about it, and we'll just make with this. This is essentially making a light noise about these things that you may have to encounter. On function spaces called the inductive limit. Then of course what we insist on topological vector space get a topological vector space. The topology is not necessarily derived from a no. See, all non-linear spaces are topological vector spaces. But the converse is not true. These are some of the remarks I want to make. So note that in this scenario, so for a topological vector space, what we insist on demand on is that the vector space operations are addition and scalar multiplication are continuous with respect to the induced topology. what we have observed is that the normed linear spaces, or more specifically the inner product spaces, do have this property, so they are topological vector spaces. And normed linear spaces inner product spaces are topological vector spaces. Now we leave that with those remarks. Okay, so let me just put here remarks. This is an important remark and a pointer to what all things we may have to later deal with, but not at the moment. Okay. So that's about a remark on the topological vector spaces. So all inner product spaces are topological vector spaces because the vector space operations are continuous with respect to the topology induced on the space. And that makes the life simple on those spaces. Now we return to inner product spaces. Later on, we will consider another problem. Okay, before that, let me also make a statement that there are normed linear spaces which are not inner product spaces. I will return to this question later. So I will make a remark. So let me make a remark here. Further remark. Inner product spaces. So it's essentially normed linear spaces form a larger class of objects. And of course, topological vector space is a still larger class. So what you have is this inner product spaces. This is the relation. But inner product space are something very special, as we shall discuss this aspect later. So we postpone it for the time being, discuss this, but maybe we will give just an example. R2 define let me just put 1 here. And this is not induced. Product. Now I will return to this problem later, because we take up this problem while considering the characterization of a normed linear space as an inner product space, or we will say what exactly, under what conditions on the norm, the normed linear space is an inner product space. That we will look at more deeply. And for the time being, I think we will just leave this remark and then proceed further. So I will return to this problem. We return to this problem. We look at it in some depth and even say under what conditions a normed linear space is an inner product space. For example, if you take this one, this is also a norm. This is a norm, and this is coming from and yeah, let me put it elsewhere so that you don't confuse with it. Note that an inner product space. So with a different norm, it becomes an inner product space. Okay. We will see why this doesn't become an inner product, this becomes an inner product. Look at some interesting consequences of a norm coming from an inner product, and then try to characterize it. Okay, that is, ask the more deeper question: when a normed linear space is an inner product space. So this is one of the things that we want to consider in detail. We'll look at some examples that we have maybe of interest. So you take V to be equal to Cl. So a typical member is this. With the usual addition of x plus y, etc. When you define yi conjugate, this is product, and you see that the norm induced by this is sigma mod in fact what we have looked at here. So if you want, you can call this 2 with a hindsight. Okay. So this is the norm, and you can show that this is a normed linear space. These are some little examples. I mean, there are a lot of examples that you can give in this context. Now on polynomials, suppose you take polynomials over C. Can take sequences S sequences Xn such that then you can show that this is, or let me use the notation. Okay. Now L2 is a vector space where you define x plus y as this is the definition. Now alpha x is equal to alpha xn alpha xn for alpha belonging to. So here all xi's belong to C. So complex sequences which are with the property that this sum is finite. A normed is a linear space. That's easy to show. Now define conjugate. Then a third example. P or polynomials with complex coefficients. With usual rules for addition and scalar multiplication. Now this may be considered defining functions, complex valued functions on the interval 0, 1. Considered as a function defined on the interval 0, 1. I'll write it as complex valued function. On 0, 1. That is P maps now with the usual addition and scalar multiplication. Yeah. Is vector space now define Now you can further generalize it and talk about all continuous functions on the interval 0, 1. Continuous complex valued functions. Now the next example is there is no sanctity for this 0, 1. You can take it as any interval of the real line. Okay. So V equal to and you see that the class of polynomials that we have looked at is a subspace of this. Again, on V we introduce is an inner product. There are various generalizations of this. So these are some of the common examples that you encounter, and there are a number of examples that you can introduce, and you can even put a weight here, weight function, a positive definite function, and define fg, inner product of fg with integral 0 to 1 rt ft g bar t dt, where rt is a real valued function which is strictly positive on the interval 0 to 1. Then it becomes a weighted inner product space. So there are a lot of examples that one can introduce here. Okay. So our objective will be to study the properties of the inner product space, and that's only the beginning. So that is preparing the ground, and after having prepared the ground, we will talk about what are called the linear maps on inner product spaces, because we have already seen on linear spaces how the linear transformations or linear mappings work, and it gives very interesting properties that we have seen already. So now what we are going to do is, in the light of the presence of an inner product, what more things you can expect. And in fact, there are a lot of interesting things that you are going to see with that background. Now we made some little calculation. We observed, suppose V is a vector space, parallelogram law. What is the parallelogram law? In R2, suppose you have a parallelogram. In a plane. Now you see that, draw the diagonals. Now what you can prove is this. B, C. You can show that OC square plus AB square by which I mean the length OB, or if you want you can do this. This is equal to twice that is the sum of the squares of the diagonals of the parallelogram is equal to the sum of the squares of the sides of the parallelogram. And because you see OA equal to BC and OB equal to AC, so we don't write it separately. So you write it as twice or distance OA square, twice length OB square. Okay, so this is what you observe. So is it valid in this general case? Let us explore this. Now let us look at the problem in R2. R2, see what you have. So in R2, so we take U equal to V1, V2. Then you see that, see OA, this is the vector U, vector V, which corresponds to what is called OA, OB. Then OC is equal to U plus V OC, the same figure. So this you call OB. OC is U1 plus V1, U2 plus V2. Now you also have so U minus V, which you write as AB. So the vector AB, I think essentially you are working out this vector and whose length is equal to AB. So the length of U minus V is equal to AB. So this is a sort of misnomer. I write this as AB. It's actually, see, you write this. Okay, this is equal to this is the vector that you have, or I'll just it's here. That's the length of a vector. Okay. Therefore, what I want to prove is this. OC square plus AB square okay. Let us work it out using the inner product. Now, using the inner product, you see that okay. Now, you see that here u square that's the definition of that in this case. Now, this is what you have, and you can show that this one OC square, that means u plus v this is equal to this is equal to this is quite simple. Very simple exercise. Just work out the inner product and then you get this result. Therefore, you see that in this case, recognizing that u1 v1 plus u2 v2 is the dot product of, or the inner product of u with v, one proves this. That is, what is this? This is equal to OC square OC square plus this is the parallelogram law is valid. So, it's a proof of the parallelogram law using the inner product. Okay. Now, what we expect is that, so in any inner product space, the parallelogram law for the induced node. This is what we want to expect. So, we are generalizing it. We are now not bothering about the geometry of the of the space, or whether it is finite dimensional or infinite dimensional, all that we assume is that it is an inner product space. That is a linear space with an inner product on that. Just move this. So, by the induced norm. Okay, so let us work on that. So let it is immaterial whether it is a complex inner product space or a real inner product space. So let then this is the parallelogram. Okay? The proof is, of course, trivial. Is the definition. That is the relationship between norm of U and the inner product, and then you can easily verify this. That's a simple exercise as we have done here. Therefore, every inner product space satisfies the parallelogram law, or in every inner product space the parallelogram law holds. Okay, and this is where we have seen that, you recall this example that I said, R2 define now now the question is the parallel law now it is sufficient to show that there exist vectors for which this is not true. Okay. For example, what happens if you choose vectors like, suppose you choose u equal to 1, 0, then what about norm u? U plus v is that for norm of 3. Okay. U minus V equal to U minus V is 0 minus 1. Now we just check whether it is true. So norm of this is equal to what? This is actually 9 plus 10. Norm of U square equal to 1 Oh, I think these vectors do not give you the result. So let us work with some other vectors. Let me work with another pair of vectors. That doesn't prove it. U plus V equal to 2 0 equal to 2 4 equal to Okay, right. Take U equal to -4 mod 416 norm of U square equal to 1 plus 2. Okay, now norm of U plus V (20). Now norm of U square plus norm of V square equal to 18. So parallelogram law is not satisfied. So for this choice of U and V, the parallelogram law does not hold. Okay. So that tells you that this particular space that we have looked at is not an inner product space, because every inner product space, in every inner product space, the parallelogram law holds. So if you have a normed linear space in which the parallelogram law does not hold, naturally it is not an inner product space. Okay, thank you very much. I think I will stop here.